Hi. So welcome back to this lecture where we will continue with our venture with second order linear ODEs, but we were doing D operator method. So we were basically looking at solving differential equations by invoking certain properties from algebra, rings and modules. Okay, and we've already set up the basic structures and the properties from algebra that we need, and which basically we are going to implement those properties and those concepts here in this field of solving differential equations, and we will look at them in that different light, and so let's just do that. So just a quick recap. So we had proved the last time that RD, which is really the set of all formal power series with D as the indeterminate or the variable, which finally, of course, we defined what D was. D meant it was an operator. D to the power I was the ith time differentiation with respect to t. So it really is an operator. It wants to act on some function. Otherwise, without that, it has no meaning. But anyway, we had defined what it was, and with constant and with real coefficients. Okay. So it was like this. So any element of Rd was of this form: a0, a1, d, a2, d squared, like that, where a0, a1, a2, they were all real numbers. And we said that we found that this was a commutative ring, okay, commutative with respect to the multiplication, okay, with R and plus, with plus sign. R is always commutative group, okay. It's a ring, but it's a commutative ring, and it has a unity. In other words, 1, which is a real number, is also an element of this ring of power series, of course, because R is included in this ring. And this 1 acts as a unity, in other words, acts as a multiplicative identity, okay? So in other words, if you take any element PD and you multiply that with 1, it doesn't matter from which side. By multiply, I mean multiply in the sense that it was defined while defining this as defining this as a structure. If I multiply PD with 1, I will just get PD, okay, for any such polynomial or power series, right? And we also found the C infinity, which was really the set of all functions which were differentiable, infinitely many times. This turned out to be an RD module, okay. In other words, this ring, this commutative ring, had some kind of an action on elements of C infinity, and that action was defined as this, okay, where PD, being an element from RD, acted on F, an element of C infinity, by this definition. So if PD was 0, it was just a term by term action. So A0 would act on F by just simple multiplication, because A0 is a real number. A1D would just differentiate F once, because there's a D here, and A1 would remain as it is before, just before D, or before this resultant function, multiplying it from before. Similarly, A2 D squared would double differentiate the function F, and A2 would just multiply it. Okay, so the action of RD on C infinity was really a term by term action of an element of RD on an element of C infinity. Okay, PD is the element of RD, F is the element of C infinity. Okay, and it turned out to be a module. In other words, it had certain properties, and we will invoke those properties as we go along, and we have discussed them before. So coming to exactly what we have to do now, we have to solve this differential equation, second order linear ODE, with any kind of input. Okay, so we've already solved some functions, some equations with very specific inputs. For example, the exponential input, the sinusoidal inputs, the polynomial inputs. So it all comes down to now solving these differential equations using the concepts that we have already learned from algebra. So one thing that must be noted here is when we are solving these kind of differential equations, the x and f here, which are functions of t, of course. That's why you could differentiate x with respect to t twice and once over here. And similarly, f on the right hand side, the external force, so to speak, was also a function of time. These two will have to be elements of C infinity. In other words, these two will have to be, differentiable infinitely many times. Okay, that's important because we are really going to involve these things here. So unless and until they are differentiable infinitely many times, we can't really invoke the properties of these two. Okay, all right. So we are only dealing with these kind of functions, x and f, which are C infinity. Now, when we say solve this, how do we invoke the RD and the C infinity here? So we look at a very specific kind of element from RD, and that is, we call that QD. It's a polynomial of degree 2. I think it must be noted here that even though a general element of RD is written in an infinite series like this, the series could be terminal in the sense that, let's say from A3 onwards, A3, A4, A5, all of them are zeros. And then there are no next terms in this series, so the term really is A0, A1, D plus A2, D square, which is only a polynomial of degree 2. So it's in the general form, it can be written, like this, but really these can be short polynomials of degree n, degree m, like that. Okay, so QD is one such element of RD, where the first element is C, the second element, the same C as this C, which we are solving. The one with the coefficient of capital D is this B, and the coefficient of D square is just 1. Okay, if I look at this element from RD, and I make this act on x is the function, which is a function from C infinity. If I make it act on x, what happens is that the way QD acts on x is term by term action, d square plus bd plus c. And what's the term by term action? So this is acting on x. The first one acts on x to differentiate it twice, because d square really means double differentiation, plus b is the constant, and d on x means x prime, and c on x is just the multiplication with x, because you see, when there's a constant, the constant term always simply multiplies the function on which it is acting. So this is just cx, and that's really the left hand side of the equation. Okay, so the left hand side of the equation can be written as the action of this particular element of RD on this function x, which we have to find, really. I mean, remember, solve this means we have to find x as a function of t. That's what we are doing. So, since it is given to solve this thing is equal to ft, we're really solving q dx equals ft. Okay? Now, this is where we are bringing in elements of RD, and therefore we need more algebra here. Okay? Now, the question is, what can we do with it? So what we can do with it can be answered by the concept of whether an element does have a multiplicative inverse or not. Okay, so the question is, so when R was a ring, we did not see any multiplicative inverse, or there was no need to discuss them. Some elements could have multiplicative inverses. In other words, so let's say what it is. So PD, if I have an element PD from RD, and if I can find another element, let me call that SD. Let's say PD is given to me, and I can find another element SD from RD, such that if I multiply SD with PD, and this gives me the unity in this ring, unity is just 1, the real number 1. If I can do that, then SD would be called the inverse of P. Okay? In this case, SD would be written like PD inverse. This would be called the inverse of P. Okay, and of course this has to be equal to PD dot SD as well. So in other words, you have to find an element SD such that it doesn't matter from which side you multiply that with PD, you would always get 1. If you could find such an SD, that would be the inverse of P. And when I say inverse, of course, remember the operation that I'm using multiplication operation. So I'm saying inverse with respect to multiplication. So multiplicative inverse. Okay. So this is invertible with respect to this, really, the dot, the multiplicative inverse. So there is a result that I'm quoting here. The result that I'm quoting is that for any PD from RD, any element from RD will be invertible with respect to multiplication if and only if the constant term in it, that is A0, is not 0. Okay, that's the result I'm quoting, and I'm not going to prove the whole thing, prove the result, but I'll give you a flavor for it. The way we find the inverse is by taking the reciprocal of, so if you have PD, so as I have done it here, so let's just give you an example. Example of QD. QD is this. So let's say QD is one kind of PD, of course. It's a special kind where after a certain term, all the coefficients are 0. But how would you invert QD is by what is known as Taylor's theorem, and I'm sure all of you know Taylor's theorem, is that, so I'm trying to find QD inverse, or Q inverse D, whatever way you want to write it. I'm going to write the reciprocal of QD. In other words, the reciprocal of QD is going to be D squared plus BD plus C. Okay, this is going to be, can I write this as 1 by QD? Okay, just for notational convenience, because I have sort of done the reciprocal of this. It's still a function of D. Okay, so I'm just writing this as this. Okay, 1 by QD. Then I have to apply Taylor's theorem on it. Taylor's theorem says that this is exactly what I've written. The way you find the inverse of P, or in this case Q, is you take this inverse 1 by Q, this thing, and you find out this whole calculation. Okay, you take 1 by P of 0. In other words, so let's do that with Q here. I'm doing with Q. So 1 by Q of 0 would really mean I have to put 0 everywhere there is D. So that is 1 by C. Let's just box that. I got the first term for Q inverse. Then I have to differentiate 1 by P, or 1 by Q here, with respect to D, of course, but add 0. Let's do that. Let's differentiate this with respect to D. So 1 by Q, I'm going to differentiate this with respect to D. This is going to be what? I'm going to get a negative sign from the index -1 here. So D squared plus BD plus C whole square. And I have to differentiate this also. So I'm going to get a 2D plus B. And let's just put, so what am I asked to do? I have to find that out at 0. So I would 1 over Q differentiated at 0 would just be putting 0 instead of D. So if I put 0, I get a 0 here. I get zeros here except for C. So I get a minus B over C square. Okay. Okay. And if I put all of them together, I would get what I have written out here. Okay. You can see the first term, 1 over Q0, 1 over P0 here is 1 over C. And the second term is 1 by 1 factorial is 1. This term, this differentiated term at 0, which gives me minus B over C squared with a D. The third term, if you do it, exactly the same way, 1 over 2 factorial double differentiation of 1 by P0 would give you this with a D square, and you continue like that. Okay. So so the way you find the inverse is using Taylor's theorem, and you can see why I said that the constant term must be non-zero. Only then can this be invertible, because when you're going to invert an element, the constant term is coming in the denominator all the time. So the only way that Q could be invertible was if the constant term in Q was non-zero. In other words, this term C is non-zero. So if you have a term like this, if you're going to deal with a differential equation where the C is non-zero, then this QD is invertible. And the inverse of QD is given by this particular element. It really is an element of RD. As you can see, it's a power series. It's a formal power series. The first A0 is a 1 over C. The second A1 is a minus B over C square and a D. The third A2 is B minus C square over C cubed D square, and it goes on. So this really, this thing is actually an element of RD. Okay, so you have found the inverse. So we're going to solve equations where C is not zero. That's also important. Okay. Fine. Now that we have established that we are solving equations where X and F are from C infinity and C is not zero, in that case, we know we can find the QD inverse by a formula like this. If you wanted the next term, you would have to differentiate it once more at 0. And the next term would be 1 over 3 factorial, 1 over P differentiated 3 times at 0, D cubed, like that. Okay. So, coming to what we are doing, we're solving this differential equation. But for QD, I have found a QD inverse given by this power series. So I can multiply, but when I say multiply, I mean multiply in the sense of the multiplication given in RD. I can multiply, no, I'm not multiplying. This F here is a function from C infinity. This also remains a function from C infinity, because you're only differentiating. QD is really differentiation of X. You're differentiating it maximum 2 times. But since X is differentiable infinitely many times, even after a couple of differentiations, this left-hand side remains differentiable all the time, or infinitely many times. So both sides are now, the entire thing on the left, and of course this one, they are elements of C infinity. So I can act on both of them, this one and this one, by an element of RD, which I choose to be QD inverse. I act on this C infinity element by QD inverse, and I act on F similarly by QD inverse from both sides. Now, remember, this C infinity is an RD module. And we had discussed this when you have a module where you have an element of the ring acting on already an action. What you can do is, you can first make the 2 ring elements multiply. So this really means, by our rule from modules, because these are elements of the ring and this is the element of the C infinity, which is a group, a commutative group, the way the action works is that you can make the 2 ring elements first multiply, and then whatever that is can act on X. Of course, the right hand side is what it is. Okay. But since they are inverse of one another, this really is 1. Because this is the inverse and it should give you 1. The unity, remember? And unity acts on X, again, by our definition of a module. A unity from the ring acts on the group element, or C infinity, by just keeping it what it is. So the fact that we had to find this function X is really given by the action of this ring element, this QD inverse, or this whole calculation on the function. And that's all there is. Okay. So the way you can find, you can solve a differential equation bringing in the rules of algebra is by finding out this inverse of the given ring element which is acting on x, and then make it act on f term by term wise, and you will have your x. So I'll just do an example here. We had given a problem in the assignment, and in fact I can just rub this out. One of the problems in the assignment was to find was to solve this equation x double prime plus bx prime plus cx equals some polynomial of degree 2, small a t square plus bt plus small c. And I called it, I think, pt or whatever, okay, because it's a polynomial of degree 2, I called it with p or capital P. I don't remember what was the name. So I had to solve this. Now, of course, and from all that we have understood that qd with exactly this q, we've rubbed that out, q dx is equal to this p, this polynomial on the right, where qd was d square plus bd plus c. And we just said that to find x, therefore, all we have to do is to apply qd inverse on the right hand side, on the input. Remember, f was the input, and the input here is this polynomial p. And what's that? So x therefore will be qd inverse. I've found a couple of terms here. It's 1 over c minus b over c square d plus b minus c square c cube d square minus dot dot dot. This whole thing acts on the polynomial p. Now, as I said, what does action mean? It's term by term action. So I can so this one simply multiplies. So I have p over c minus b over c square. This is just the differentiation, one-time differentiation. So ddt of p, the polynomial. Then b minus c square over c cube. This is the two-time differentiation. And like that. However, if you act the next term on p, you're going to get a 0 because the next term has a d3 in it, d cube in it. And d cube means triple differentiation of a polynomial which is of degree 2 gives you 0. Similarly, the next to the next term, which is a d to the 4 term, even that fetches you 0 from a polynomial of degree 2. So the next terms are not there. They're all 0. And can you remember this formula? This was, I said, this was the particular solution. This was the particular, the question was to prove that this was the particular solution for this differential equation. And of course, you could just put in here and show that it comes to this. That's all right. But really what it comes from is the application of the inverse of this QD given by Taylor's theorem, okay? And if you do that term by term action, you will get the XP straight away without hassles, okay? And that's just plain and simple how you bring in algebra and the fact that some elements can have multiplicative inverses. And once you find the inverse, it's just term by term application and you have the answer. Okay, so I think we'll finish with this one here. Just an example. We will do a couple of more examples of a few more inputs which we have learned. This was one of the inputs which we have done. We'll do a couple of more inputs and show them how they pan out in this new light from that we have shed from algebra. So I think we'll finish it here. Take things forward in the next lecture. Thank you.